So, gentlemen, now this is the topic, and the next 1 hour we are going to talk about refrigeration, marine refrigeration, and the objective. In fact, I request participants, especially this has been mainly for MEO students who are taking for the MMD examinations at class 2 level. And in my presentation, I have also included some specific questions that are being asked both in orals as well as in the written paper of MEO class 2. So the students who are listening to my lecture, at any point of time during my presentation, you can just stop me, you can interrupt, and you can ask your questions. And don't keep your questions right till the end of the session. And I will appreciate if you can just ask me then and there, so I'll be able to explain. So the objective in the next 1 hour, we are going to talk about learner understands marine refrigeration, air conditioning, designs, systems, and equipment. And as I have said, let's first focus on refrigeration. So refrigeration, as all of you are aware, on board the ship, this is one of a very important utility. In fact, for people who stay on board, we have meat room, we have fish room, we have vegetable room, about which all of us are very familiar. But the rooms are kept at different temperatures because we don't want the food to get decayed, because the ships on board we do long voyages, and the foodstuff, whether it is a vegetable or whether it is meat or fish, it requires to be kept at the different stipulated temperatures, otherwise it will decay. So let's just go one by one. What is the basically refrigeration principle? Because refrigerators, yes, all of us we have at home, domestic refrigerators, and on board we are talking about, here the focus mainly is going to be marine refrigeration. That means on board the ships, how the refrigeration system works, and how the refrigeration plant, what sort of maintenance we do, and basically how the system works, and what the troubleshooting part of it is very important. And basically, what do we do? We cool things like meat room. We keep somewhere between minus 15 to minus 20 degrees centigrade. And of course, fish room is also very similar, minus 15 to minus 20. And if it is vegetable room, then we cannot keep it at minus. So we need to just come up to probably to plus 3 to plus 8 at the most. And of course, we have a compressor. Basically, what we follow on board is what we call vapor compression cycle. It's a thermodynamic cycle, or people call it reverse Carnot cycle. This is the basic principle. As you can see, lower temperature is required to preserve food and all that. And vapor compression refrigeration, I just mentioned it. And what the refrigerant does, see, can we use anything as refrigerant? Like, for example, let us look at the marine refrigerants, what we are using presently on board. In olden days, we were using what we call CFCs, we used to call it R11 and R12, things like that. And then from there, we slowly switched on to what we call hydrochlorofluorocarbon. Earlier, it was chlorofluorocarbon, which has been banned now. And then we moved on to hydrochlorofluorocarbon. And as mariners, if you just look back to MARPOL Annex 6, what does it say? We have a Regulation 12. The Regulation 12 of MARPOL Annex 6 very clearly talks about ozone depleting substances. Because refrigerants like CFCs are ozone depletion. As all of you are aware, ozone means a sort of a layer, maybe about say 50 nautical mile around the globe. We have a layer which is supposed to prevent the ultraviolet radiation onto the Earth's surface. So all of us are protected. So in case if ozone depletion occurs, then it's going to cause a lot of problem, health issues, and of course, people talk about skin cancer and all that. So your regulations around the world, whether it is maritime regulations by IMO or UNEP, various regulations, they put stipulant, what type of refrigerants that can be used. So CFCs is out now. So as of now, we move on to hydrochlorofluorocarbon. That R22 happened to be the refrigerant we normally used. Of course, we have been using it there. Now, Annex 6, in fact, from 1st January 2020, they have put a stop for R22. So basically, now we need to move on to hydrofluorocarbon. Let's see the difference. Hydrochlorofluorocarbon. Now it is hydrofluorocarbon. So the concept is the chloro the chlorine or chloride related anything is harmful for ozone depletion. So basically a refrigerant, if you just look at the basic fundamental question, what is a refrigerant? Refrigerants, as you can see, we use it in the refrigeration system. Basically, it keeps getting converted to liquid as well as to vapor form. So you take any of the refrigerants, even domestic refrigerant, what does it do? We have a compressor, as I have said, vapor compression cycle. And of course, the other system, what we used to have is vapor absorption cycle. This vapor absorption on board the ships, as of now, we are not using it. Like, for example, we see ammonia we used to use as a refrigerant. That means anything can be used as a refrigerant as long as it gets converted to vapor and condensing it into the liquid form. But certain conditions apply. This, like, for example, on board when we use refrigerant, if you use the condenser where we condense the refrigerant, the condensing medium or the cooling medium happens to be the seawater. So that means the seawater, what is going to be the temperature of seawater? Okay, seawater temperature can go down, maybe 5 degrees. Suppose if you are in somewhere in colder region, or in tropical region, if you come up, somewhere around 32, 34 at the most, but it's not going to go more. So since we are going to use seawater as a condensing medium, so we need to, select a refrigerant which is compatible to the seawater conditions. So as of now, if you are looking at hydrofluorocarbons, now look at these refrigerants. These are all the refrigerants, what we call blended refrigerants. In fact, eco-friendly and low ODP. ODP stands for what? Ozone depleting potential. Ozone depleting potential for all of these refrigerants presently, what we are using, like 404A or 407C or 134A. In fact, 134A is being used on automobile air conditioning system also in all the cars now around the world. And 410A. So these are all the common refrigerants nowadays you will find on board. And of course, as you can see, ODP of all these refrigerants, because ODP we always we refer, if you take R11 chlorofluorocarbon R11, that happens to be, if you take ODP as 1, these refrigerants, they're all having 0, because if you have 0, that is the ideal condition. And the other one is what? Global warming potential. Always it denotes the benchmarking value of carbon dioxide. Carbon dioxide, if you take 1, because these are all the values what for various 1400, 1610, it's higher than CO2. But ideally, a refrigerant, like can we use, for example, ammonia as a refrigerant on board? Any of the participants can give me a reply? Ammonia, can we use? Hello?
We have used in fishing trawlers, sir, long time back.
Oh, okay. Ammonia you have used in fishing trawlers. But why is it not recommended for ships use, maritime use? In marine refrigeration system, I don't think we have any of the ships we have.
Sir.
Yes.
Toxic.
It's toxic and flammable.
Yes, you are right. Because it is toxic. Because if you are looking at, so that means, then we need to look at what are all the qualities, what properties we need to have a refrigerant. That means anything. Okay, can we take carbon dioxide as a refrigerant? See, as I have said, the fluid should turn into both phases. That means the phase change, either to liquid form or to vapor form. Suppose if you take carbon dioxide, yes, we can liquefy it at of course, conditions apply. Can we use carbon dioxide as a refrigerant? Then what are the advantages or disadvantages? Yes, anyhow, I have a slide on. Yes, sir. Yes,
static electricity possible.
Critical temperature.
Anything else?
Critical temperature.
Yes, critical temperatures. As I have said, if you see the critical temperature of carbon dioxide, it is somewhere around 31 point something. You take it as 31. Okay, suppose if your seawater temperature is let us say 33, 34, then what will you do? So then we need to understand the basics. We will just see. Now the present refrigerant, I'll come back to carbon dioxide. I have a slide on that. Now these are all the refrigerants, what we call the blended refrigerants. Different. What I have listed here, you can see it in the screen. These are all called geotropic refrigerants. The geotropic refrigerants do not boil and condense at constant temperature. Just read the last sentence there. That means when they vaporize or when they condense, there is a little bit of difference. There is what we call glide. This glide is, experts say that is to our advantage. That keeps the efficiency higher or the pressure range. But anyhow, if you see the blended, like many ships nowadays we are using R404A. Now, what is 404A? Now look at the ratio. We have 125, 44%, and 143A, 52%, and 134A, 4%. So it's all blended. That means when you have a blended refrigerants, the phase change should occur at the same time. But that the difference may be there. That is what I told you, just gliding. But then, they are eco-friendly refrigerants. So that's the reason we are now using it. Now let's look at carbon dioxide, what I mentioned. If you use carbon dioxide, if you see, now look at the discharge pressure. Now, when you have a compressor, but the present refrigerants, whatever we have selected, so mariners, you understand, what do you, what is the discharge pressure of your compressor? Anyone can tell me? Let's say 404A you are running, or R22 you are running, maybe. What is the discharge pressure?
14 to 16 bar.
Oh, okay, 14, yeah, around 16 bar. But if you use carbon dioxide, because then what is going to be the pressure to what pressure? You need to pressurize it to use seawater at 31 degrees to condense it. You see the saturation temperature at the corresponding pressure. In fact, if you are using somewhere around 30, 31 degrees, 30 degrees seawater, even assuming that you are getting seawater as of now at 30 degrees, then the pressure range is going to be very high. It's going to be somewhere around 76 bar. So if you see the last line in the presentation now in the slide, the main problem with this refrigerant is its working pressure is so high. So the compressor needs to be designed accordingly. And what about on the compressor discharge side, what you are having? You are having a discharge valve, and after discharge valve, discharge pipes, and you have a oil separator, and oil separator, the pipelines lead to the condenser. And at condenser, at what is going to be the pressure? It's going to be the same pressure. So condenser, liquid receiver, then from the liquid receiver, it right up to the expansion valve, it's going to be what we call high pressure side. Now in the high pressure side, it is going to be, the 76 bar is practically not possible. So that's why we are not using carbon dioxide. Of course, shore side you can see, ammonia related or even carbon dioxide related. But of course, you are from but you can call it a eco-friendly refrigerant, carbon dioxide. So basically now, when you look at the refrigerant properties or the qualities, what are all the qualities? There are some thermodynamic properties required when you select a refrigerant. We are looking at latent heat of sea. If you see the low boiling point, freezing point, and of course condenser pressures and critical temperatures and pressure. As I have told you, carbon dioxide has got 31. That means in case if the seawater temperature happens to be 34, then if you use carbon dioxide, it's not going to condense in the condenser. So it's you'll not be able to use it. Then apart from that, what are the other things? Safe working properties. And somebody, you said no, the ammonia is what? Toxic. So here, what we need to select a refrigerant, it should be non-flammable. It should be non-toxic. It should be non-reactive. It should be inert. So these are all the requirement. Okay. Now physical properties. You see, specific volume needs to be lower, specific heat of liquid, and increase the refrigerating effect per kg of refrigerant. Now again, when you are looking at the refrigerating effect, I'll just to show you. Always, when you look at the fundamentals, the basic concept of refrigeration, we need to look at what we call Molier's chart. Molier's chart. What is Molier's chart? Anyone can tell me? What are the parameters we have in the y-axis and the x-axis of Molier's chart? Any one of the students there?
Pressure
on one, yes. On one side you have pressure. The other side you have
pressure. Enthalpy.
Okay, so we call it pressure enthalpy diagram. Yes, I'll show you one. So, then what are the other properties? We'll go back to enthalpy a little later. Now that low viscosity, heat transfer, viscosity, and either both in the liquid form as well as in the vapor form, it needs to be, heat transfer should be more efficient. other properties, odor, compatible with system. See, this is a very important point. It's compatible with system lube oil. So you just look at a fridge compressor. What sort of oil you are using? Like different oil companies, they come up with different names like Ismatic or Zero, whatever lubricating oil that you are using. Your lube oil pump is going to run, and one thing you must always remember: in a fridge compressor or your AC compressor is very much different from your main air compressor. Your main air compressor, you have, it is vented to the atmosphere. But your fridge compressor, can you vent it? Or in your AC compressor, can you vent it? So in fact, your fridge compressor crankcase happens to be the reservoir for storing the refrigerant, which is coming back from the evaporators. And of course, when the piston goes down in the compressor from the reservoir or crankcase, the refrigerant enters the cylinder. That's how it works. So the refrigerant is always above the lubricating oil. So compatibility should be there. And of course, depending upon the compressor running and all that, some of the oil fumes may enter and it may get discharged along with the refrigerant. Of course, we have an oil separator, and this oil separator, so the probably the emulsion part of it may occur. So it also needs to have a proper demulsibility characteristic, so that when conditions correlate, the oil and refrigerant should get separated also. So these are all the things compatible with system lube oil. And the next one, what I have written, COP. What is COP? Is it cargo oil pump?
Coefficient of performance.
Coefficient of performance. So what is it? So let's just look at 1 minute. Coefficient of performance. We briefly write it like this. So COP is what? Refrigerating effect divided by heat of compression. Now,
Sekhar sir, you want to ask any questions now? Take any questions?
Yes. Yeah, if any of the participants, if you have any questions, please tell me. I am waiting. Any of you have any questions?
So there was one query from Mohit Kumar. He wanted to know, please explain with the help of a diagram.
Yes, I'm going to do that. My coming slides are on pressure enthalpy diagram. I will do that, and that time I will explain the COP also.
Okay, sir. Okay. All right, sir. Okay.
Okay. Now, regarding COP, yes, I'll just show it in the coming slides. And what sort of lube oil we need to have? You see, the AC and fridge compressors. Yes, we have lubricating oil. We have a lube oil pump also. Lube oil lubrication is required for the bearings in the crankshaft. And what are as you can see, stability is very important. Of course, pour point, because what sort of temperatures this refrigerant and oil mixture will get exposed to. Or dielectric strength. But sometimes what happens in your engine control room, air conditioning system, have you seen? We have a hermetic compressor there. The hermetic compressor, where is the compressor? Compressor is also in that black box. That means your oil. So dielectric strength, the appropriate dielectric strength it needs to have. Otherwise, the oil is going to be in direct contact with the windings. And flock point. Okay, anyone? I just put a question now. Can anyone explain me what is flock point? Pour point, yes, all of you know. That's very, very fundamental thing. What is flock point? Any one of the students?
The temperature at which wax crystallizes.
Yes. Who's that? Who replied me? I'd like to know the name.
Ishad.
Ishad. Ishad. Yes. So that's what it is. That means, you can say wax precipitation, because your lube oil is, will be exposed to a very, very low temperature. And at low temperature exposures, what you will see, so the lube oil, what is used for your fridge and AC, it has been the basic oil and it has been formulated, additives have been added. So there is always a tendency to precipitate, the wax precipitation will occur at when it is exposed to a lower temperature. And of course, we have a similar thing, when lube oil not exposed to very low temperatures, we also have an equal thing, what we call cloud point, you may be knowing. So flash point, neutralization number, of course, oil compatibility. And now what you are looking at, now this is what is your pressure enthalpy diagram. I think one of you wanted to see this diagram, just look at this. Now pressure on the y-axis. And this the pressure enthalpy diagram of R134A. one of the hydrofluorocarbons. So as you can say, now can you tell me what is this particular point right on top? Now you see, now this is the line. You can call it a saturation liquid line. And here it is your saturation vapor line on the right hand side. Now right on top here. Now what is this?
Critical point.
Critical point. Critical point.
Critical, yes, critical point. You can say critical pressure, and of course, you see the temperatures. How do they come? See, the temperature comes right like this, and then it just exits. So you can see the critical temperature and the critical pressure. So this is for a typical 134A. Now this is what is happening in a cycle. Say, suppose in our on board the ship, how do we have? Now look at this pressure enthalpy diagram. I think it's very clear here, and it's the same diagram. So whatever may be the refrigerant, it's going to be something like this. And look at the point 1 and point 1 dash. So now this 1 dash is going to be the point where compression takes place. Okay. Now what I'll do, I'll just go. See, these are the main components of our marine refrigeration system. Is it clear? You have a compressor. What does the compressor does? It draws the refrigerant from the evaporator. The evaporator pressure may be very low, around 1 or maybe less than 1. In fact, you will find when all the 3 rooms are in use, like your fish room or meat room or vegetable room, when all 3 rooms are working full, you will find your suction pressure of your compressor is somewhere around 1.8, 1.1, something like that. And accordingly, when the rooms get cut out, then you will find accordingly the suction pressure reduces. So the compressor compresses it. You have said, okay, 12 to 14, 15, or depending upon the refrigerant, you have a discharge pressure, and then it goes to your condenser. That's so in condenser, what is happening? That's where the phase change is happening, and it is supposed to take place at the constant pressure. Is there going to be any difference between the vapor pressure and the condensed liquid pressure refrigerant? So
No,
the
sir.
No, there will not be. So then you have a receiver, and then from the receiver you come all the way right down here. Of course, now this is where it's a schematical representation, and then you have an expansion valve where from so through, of course, after the receiver you may have a filter, and after the filter it just comes. So it's just a schematic diagram. And then what is happening here? Now you see C and C dash, and from C dash to D. So from C dash to D, what is happening? That's where compression is taking place. Now this is the low pressure, suction pressure. This is the discharge pressure. And then when it is exposed to low seawater temperature, what is happening? From D to E, and at this point it is having a superheat. Now in the meantime, let me just ask you, can anyone tell me what is a superheat? The definition of a superheat? Any one of you? What is superheat? Always, now from C to C dash, I told you is superheat, and A to A dash is what we call subcooling. Subcooling and superheat. Now, what is the superheat?
The
Temperature above saturation temperature heated up.
Yes, the temperature of the vapor above the saturation temperature at the corresponding pressure. That is what is called superheat. Likewise, when you are talking about subcooling, the temperature of the liquid below the saturation temperature of the corresponding pressure. Because if the pressure varies, then the temperature, saturation temperature also will vary. I think you have all, all of you have seen it in the freshwater generator. You see at freshwater generator, at what temperature your water evaporates? Anyone?
70.
All of you. Is it 70, 80?
45 to 50.
Yes, 43, 44,
0.4.
45. It is not 70. It's in the atmospheric pressure, it is 100, but not here. Okay. Now, let me just show you this. Now, this is how it is. In a very simple diagram here, you can see compressor, and you see the low pressure side, and you will see the high pressure side. Now, the low pressure side is this one, and high pressure side, compressor. From compressor, okay, condenser, receiver, and this entire side is what we call high pressure side, and this is vapor, and the liquid vapor phase is here. The vapor is slowly getting converted to liquid, and then in receiver you have 100% liquid, and then from the liquid receiver, where does it go? It passes through the expansion valve, thermostatic expansion valve, and then it just moves on. But here is high pressure, here is low pressure. Now this is what is happening. And now let us just look at a very a typical maritime. This is what we have. I think all of you must have come across this particular diagram in which book? Auxiliary. Auxiliary Machineries by. Can anyone tell me what is the name of the book?
Megger.
Megger. Yes, you are right.
Read series, sir.
No. It is not Reed series. It's not Reed series. No. You're talking about Reed's.
A small one.
EKGM. Okay. Now see, if you see, this is what we are having. See, where is the compressor? Compressor is here. Discharge pressure. Now, just looking at the diagram, tell me which are all the safety cutouts. What are the safety devices we have in this circuit? One is the suction LP control. LP control is one. Okay. And what is the other one? High pressure cutout. And what is the third one you are having? Lub oil, low pressure cutout. These are the main. Yes, master solenoid you have, and okay, motor control. Okay, now this one I need not explain to you. It is actually, you all know this. So this is the condenser, of course, receiver, then master solenoid, then it comes to the dryer. Of course, this is where we do the charging. Of course, siphon glass. Now suppose if a unit, if the system is fully charged, it is not undercharged, it is not overcharged, there is no air in the system, and everything is perfect, then this siphon glass, you might have seen it on board your ship. How should it be? Should it be with bubbles, or it should be full with liquid?
Without
Liquid.
bubbles.
It should be without bubbles.
It should be without bubble. Okay, then comes your solenoid valve, then comes your thermostatic expansion valve. Now this solenoid valve. Now see, in each room, as you can see, how there is a, how this thermostatic switch, a thermostatic switch, it has got a sensing bulb here. Now the sensing bulb senses the temperatures of your individual rooms, and your thermostatic switch accordingly, once that particular, see, usually as I have said earlier, your meat room and fish room is between -15 to -20, most of the ships. Okay, -20 is what we call cutout, and -15 is cut in. So your veg room is between, let's say, 3 to 8. So +8 it cuts in, and +3 it cuts out. And this is where, this is how a typical system looks like. Of course, you have a defrosting element. Of course, defrosting is required. You have a timer clock and all that. And this diagram is very. Any questions in this diagram? Any one of you participants? No?
Sir, I have a question.
Yes.
Sir, actually, we see that during the discharge, after the discharge side, the temperature is much higher. The and in the condenser, that is getting cooled. That is getting liquid.
Yes.
So that phase change is taking place. So how that at least the seawater temperature may be around 30 degrees centigrade.
Yes.
And the compressor discharge side temperature is much higher.
Yes.
So how it is getting liquid? That's my question.
See again, it is the same thing. See what is happening. Every refrigerant has got what we call pressure temperature chart. This pressure temperature chart will vary from one refrigerant, like R22, you will have a chart, R134 or 143A. Because what is happening, always you need to understand pressure and the saturation temperature, boiling point, it just depends upon the pressure. As I have said earlier, at atmospheric pressure, the boiling point of water is 100 degrees centigrade. Whereas when the freshwater generator, when you reduce the pressure, you are under vacuum in the freshwater generator.
Yes, right.
So there, what is happening? The evaporation takes place not at 100 degrees. Now you said that it is taking place at 45 degrees or 50 degrees. So what is happening? That the temperature, the saturation temperature. So as you have said, by the time the refrigerant comes out here, the temperature may be about 85 or 90 degrees centigrade.
Right, sir. Right.
When seawater cools it down to 30 degrees, then what is going to happen? From 90 degrees, the boiling point of the refrigerant, it just converts it to liquid. So that's what is happening. Like, for example, you take steam. Steam, when it is a superheated steam at 110 degrees centigrade, it is water vapor. You call it superheated steam. Then suppose if you cool it, then what is happening from 110, 105, 102, 100? Then when it comes, when the temperature drops below 100, but provided the pressure is 1, then what is going to happen? below 100, slowly it turns into liquid. No. Is it understood? The participant who asked me this question?
Yes, sir, I got it, sir. I'm Devashish, sir.
Okay,
Thank you,
Deva?
Devashish.
Devashish.
Sir,
Okay,
Thank
have
you,
you
sir.
understood this?
Yes, sir, I
Okay,
understand.
sir, I have a
thank you.
doubt.
Okay, yes. Yes,
Sir, in the previous
please.
diagram.
In
Yes,
this
sir.
diagram? In this diagram, or you want me to go back to the diagram what I was
The next
doing?
one. Yeah, the main diagram. The diagram, the whole diagram.
This
The
one?
next, yeah. In this one, sir. Sir. In this one, after the evaporator, to the compressor, where can we superheat the vapors?
No. Come again. Between the compressor?
So, between the evaporator and the compressor, where can we superheat the vapors?
Oh, evaporator and the compressor. But
Yes, sir.
evaporator, what is happening? You see, up to this, your high pressure. See, now the compressor, compresses the refrigerant, and it is going to be at 14 bar or 16 bar pressure up to the condenser in the vapor form. At the condenser, what is happening? It is exposed to seawater temperature of 30 degrees or 25 degrees. So here, at the same pressure, it condenses at the same pressure. That means you will have 16 bar refrigerant in the liquid form. So this is also high pressure. Then from the receiver, it comes down all the way. Here also, same liquid comes at high pressure, right up to the expansion valve. So what is happening at the expansion valve? Now, let me just go back 1 minute. I'll just to show you this. Probably you will understand this. Now, this is what is your expansion valve. Now, please understand, this expansion valve is also known as constant superheat valve. Please remember this term, constant superheat. That means what is happening now? Your high pressure liquid enters at this point. Now here, there is a diaphragm here, as you can see. Now the diaphragm has got, three forces acting. One on top. Now one on top, you see this arrow here. Now what is this pressure? This is what we call bulb pressure. Where is the bulb? You go all the way here. Now the bulb. You must have seen evaporator outlet side, you have this temperature sensing bulb is fitted. I think people on board ship, you must have noticed it. You put a clip or whatever, and in the horizontal, this is it is there. Correct. Now this bulb pressure is acting on top of the diaphragm, and the bottom of the diaphragm there are two forces acting. One force is what? Look at the spring. Now the spring pressure, which can be adjusted by this adjusting screw. But then, gentlemen, please remember, on board many times as a chief engineer or as a superintendent, when I visit ships also, I used to see people used to play around with this. But I think your chief engineer or second engineer must have told you should not play around with the spring pressure. We are not supposed to touch this. It's all factory set. And if at all it requires adjustment, probably your chief engineer will do it. But any change you do it in the spring, it takes a long time to reflect. At least you need to wait for at least 1 hour, I would say. And I think usually expansion valves and nowadays the Danfoss ones, most of the expansion valves are Danfoss company supplies. There are of course Japanese equivalents also. You may not have problem, but still one is the spring pressure acting up. And what is the other pressure? The other pressure is, please remember, condenser inlet pressure. So your condenser, not evaporator. So evaporator inlet pressure. So evaporator has got, now you see inlet pressure here and outlet pressure. But basically what should happen? It should happen at the same sequence. Like for example, now if you just look at this diagram, you will understand. Let's have a look at this, then we will go back. Now see, let us start from here. Now this is the point C dash where the compressor starts compressing, because this is your compressor starts here, C to D. This is what is called heat of compression. Now earlier I told you I will explain about coefficient of performance. Now let's look at this. Now what is written here? Heat of compression. Heat of compression is from C to D. Heat of compression. Can you see this? Because this is enthalpy and this is pressure. Now, gentlemen, please understand, you need to have a very clear understanding of this diagram. Unless otherwise you understand this, then only the principle of the conversion to liquid or conversion to vapor at different pressure, different saturation temperature, you will be able to Understand? And again, I'll just come back, after a couple of slides, there is a slide on back pressure valve. Very often I find, whenever I go for orals, people, when this question is asked in your written paper or in your oral paper, many students make mistakes there. What is a back pressure valve? Why is it fitted only at the outlet of vegetable room evaporator? Why is it not on meat room? Why is it not on fish room? These are all the normal questions are being asked in orals, but then many students make mistake. I think we will, once you understand this, Mollier, this is another name is Mollier pressure enthalpy diagram, then you are very clear in your thought, so that facing the examination will become very easy for you. Now see, from here, C to D, this is what a compressor does the work. Now this is what we call heat of compression. This happens to be the numerator of your coefficient of performance formula. What is coefficient of performance? Coefficient of performance is equal to refrigerating effect divided by heat of compression. Where is heat of compression? Heat of compression is here. Where is refrigerating effect? Refrigerating effect is from here to this. Anyhow, let us start from C. C to D is compressor compresses, and D to E slowly in the condenser from the superheated vapor, it comes to E is the saturation point, and this is called the saturated vapor line. From superheat comes saturated vapor. That is what is at E. Then from E, the seawater keeps on cooling it. See, condensing 30 degrees centigrade, and finally it comes to F. Now this point is saturation liquid line. See the difference: saturation vapor line and saturation liquid line. And at what pressure is there any? See, now here it is liquid, 100%. Sorry, 100% vapor, saturated vapor. Here it is superheated vapor. Now here it is saturated liquid. But at what pressure? You need to understand. Your condensing is taking place at constant pressure. What pressure here? It is 11.92. You take it as
of compressor.
Huh?
At discharge pressure of compressor.
Yes. You are right. At that pressure, you take it as 12 bar pressure. Everything is 12 bar. See, here it is vapor at 12 bar. Here it is liquid at 12 bar. But what happens depending upon the seawater temperature? What may happen? It may go further from F to A. This is what is called subcooling. This subcooling, what did I tell you? Definition of subcooling is the temperature of the liquid below the saturation temperature at the corresponding pressure. Remember that. So now this is what is called subcooling, and always remember condensing is taking place at constant pressure, and this is what is this? Expansion. From A all the way you write down, you come down from 12 bar pressure, you are coming down. What is the pressure here? 1.32. That means from 11.92, you are coming down to 1.32. Now the A to B is taking place at constant enthalpy. That is what we call expansion. That is what is happening in the thermostatic expansion valve. From high pressure, it comes down to the low pressure. That is your D. Now, once it enters, this is the point, where it is entering the evaporator entry point. Now, the rest of the evaporator, this keeps on at the same pressure. Again, at constant pressure, your evaporation is supposed to take place. Now, it comes back to C. Now, if you take from here, from B come all the way right down. Now, the B dash is what we call flash gas. Now, why this flash gas is occurring? Because when from high pressure to low pressure, when you just expand, temperature drop will happen. Now, that is what is reflected here in the case of flash gas. So you come down. So what is the refrigerating effect now? That means from B all the way to C dash. B to C dash is refrigerating effect, which you can see at the bottom, divided by heat of compression. Please remember this value. Usually the refrigerant needs to have a higher COP when you are selecting the refrigerant. If you are having somewhere around 4.1, 4.2, 4.3 is good enough. Suppose if it is 3.1, I think then the refrigerating effect value is less. So one of the factors which decides which refrigerant we choose, depending upon this particular very, very important point. Now, is it understood to all of you, or any questions? It's the same thing here. Now I think this diagram is more clear, so you will be able to see. So what is heat of compression? Heat of compression is 1 dash to 2 dash. Okay, then condensation at constant pressure, and then from 3 to 4, what it is? It is expansion. You can see here expansion. So from 4 to 1 dash. So now what is refrigerating effect here? 4 to 1 dash. From 4 to 1 dash is refrigerating effect, and 1 dash to 2. You need to come down all the way right down. That means in terms of enthalpy. So refrigerating effect divided by heat of compression is what is called the coefficient of performance. Any question, gentlemen? Please tell me.
Sir, in the previous diagram, sir, sorry, sir, I'm Devashish. In the previous diagram, then C to C dash is the degree of superheat.
Yes. This is, yes, 1 to 1 dash. But in the previous diagram, it was C to C dash. Yes, you are right. You are right, Devashish.
Okay, thank you.
This is called superheat. And the refrigerant always, what did I tell you? Thermostatic expansion valve is also known as constant superheat valve. That means, come what may, you need to have the same superheat. And again, after a few slides, I would like to explain about very frequently asked another question, both in your orals as well as in written, is what is the difference between internally and externally equalized thermostatic expansion valve? Am I right? These questions are being asked.
Yes, sir.
So that we will discuss little later. As of now, this one, is it understood?
Sekhar sir, there were a couple of queries
sir.
in the chat.
Yes.
Yeah, the first thing was, what is the function of receiver? This was asked by one of the participant.
Liquid receiver is actually to receive the refrigerant in 100% liquid form, because what is happening in condenser, if you see, it is usually you have shell and tube type condenser you have. That means the condenser, when the refrigerant enters at the top of the condenser, that's where the condensing is taking place. You will have more of vapor. Somewhere half of the condenser, it is slowly turning into liquid. So the bottom of the condenser, you will find the liquid is just condensing. So from there, when it drops down to liquid receiver, with the subcooling effect, what will happen is in the liquid receiver, you will have 100% only liquid. Whereas in the condenser, you have a mixture of vapor and liquid, vapor on top and liquid at the bottom. And you will notice in bigger refrigeration systems, we have a liquid receiver. And there are some small ships you will find, you may not even see a receiver. You may have only condenser. From the condenser, it may go to the expansion valve. Have I answered your question? Liquid receiver is just a reservoir of liquid refrigerant at high pressure.
All right.
Okay.
And so there was another query from Amol. Can we have an ideal temperature and pressure at each component, that is compressor inlet, outlet, evaporator inlet, outlet for R134A?
Yes. Let him look at this diagram. Please study the diagram. So this is I have taken it for R134A. This is one of the eco-friendly refrigerant. Now see here, compressor is there, and the pressure temperature chart, what I was talking about, you see the compressor suction pressure is 1.1 bar and discharge pressure is 10.9. So pressure temperature equivalent to 10.9. From where did he take this 10.9? From the chart. But what exactly is the actual temperature? 93.3 degrees centigrade. You see the compressor discharge temperature here. Compressor discharge pressure is 10.9. But what is the temperature? 93.3 degrees centigrade. But how much is the superheat here? Because at this bar, at 10.9, what you must understand, if the temperature goes below 46.1, then what will happen? It will turn into, come on here, complete my sentence. So, as you have seen here, at every stage you will see the PT equivalent, pressure temperature. This has been taken from the chart. At 10.9 bar, what is that? If you see the pressure temperature chart of 134A, you will see this. So here is superheat. Then when it comes to the condenser, now just study this condenser. Condenser again at same 10.9 bar pressure. Now what is the measured temperature here? 46.1 in the condenser condensing. Because 46.1, here there is no superheat, there is no subcooling. Then the liquid. Now if you see here, this one is vapor. Can you see my arrow moving, Subra? Yeah. Okay. Now this is the vapor. Vapor is dark. You can say black, and this is a liquid, and here it is a mixture of vapor and liquid. Now that is what is happening here. And finally here, at the bottom of the condenser, you will find it is 100% now liquefied. Now this liquefied refrigerant comes all the way to the receiver. So somebody asked the question. What is the difference between a condenser and receiver? Now look at this diagram. Now in the condenser, what is happening? Here it is vapor. Here it is vapor pressure liquid. And here, right at the bottom, it liquefies. But whereas in the receiver, you will find it has only liquid. And here it is, what is the pressure? There is a slight, in fact, ideally condensation should occur at constant pressure. And from the receiver, what is happening next? Okay. Now from the receiver, where does it go? From the receiver, it comes all the way, and finally it comes to the expansion valve. See that expansion valve, and at expansion, beyond the expansion valve, it gets into evaporator. And here, what is the pressure here? Before the expansion valve, 9.7. And after the expansion valve, it is 1.2. That means what is happening? The expansion is taking place. It is expanding. Expansion from 9.7 to 1.2. Now, when it comes down, when evaporation takes place, it requires heat to turn into vapor. From where does it take the heat? It takes the heat from the rooms, your meat room or fish room or vegetable room. That is why the temperature drops. Is it clear? Subra, is it all right? Or 134A, one of the candidates, he wanted to just...
Yes, correct. Clear, sir, clear.
Is it okay? Can we go to the next slide?
Yes, sir. There was another query from Mohit Kumar. He wanted to know what is the reason for high discharge pressure.
What is the reason for high discharge pressure? Now, just you take any vapor and compress it. What will happen to the temperature? Like, for example, his question is, temperature, high temperature or high pressure? A compressor is supposed to compress and increase the pressure. Like, look at your main air compressor. Main air compressor, what is happening? Your atmospheric air and atmospheric temperature, atmospheric pressure, air is drawn through the filters into your main air compressor. And then what does this main air compressor, what does it do? So it compresses. And have you seen the, discharge side of your compressor? You just, generally you may see a lagging, heating and all that. And without lagging, if you just feel it, it will be very hot. So whenever any compression of any vapor takes place, it becomes heat. It becomes very hot.
Yeah. Okay.
Is it okay?
Mohit Kumar, is it okay? Is it clear? I think
Mohit Kumar, is it clear? Have I answered your question? Huh?
Sir, he was asking about why the discharge pressure, if the normal working pressure is 14 to 16 bar, then why the discharge pressure is increasing to 21 to 24 bar?
Where is
Sir, he's asking about, excuse me, sir, some troubleshooting he's asking, seawater temperature, choking of condenser, something like that. He's asking about, I believe.
Oh, okay. Say, you mean to say when the pressure, when compressor is working normal, all right, you will have that 14 bar pressure only and the whole system is working all right. But sometimes you will find your high pressure cutout trips your compressor, because that is one of the safety devices. Okay, now that you have asked me, now let me just...
so I think we can leave that.
Happened?
For the next class? Yeah, for the next class, we can leave the fault finding. We have only 10 minutes now. So I think we can go with 1 or 2 more slides.
Okay, 1 or 2 more slides. Gentlemen, just have a look at this, and then this will give you this I have taken an example of R22, but it's going to be more or less similar. I would like to the participants, especially students, just to look at the temperatures. Like, where is the compressor? Compressor is here. Okay. Now suction line and of course discharge line. What is the pressure? 11.92. And what is the temperature? At this pressure, the refrigerant has been compressed and the temperature is 90 degrees. Now discharge, very high temperature, it comes to condenser, and in condenser, what is happening? 80 degrees. Then in liquid receiver, 25 degrees. So how does the liquid receiver helps you to get that subcooling effect also? Okay, now from the liquid receiver, it comes all the way through the flow control expansion valve, and now look at this point, it drops down to 1.32. That means from 11.92, it comes down to 1.32. That means just look at temperature. What was the temperature here? 25 degrees. Now what is the temperature? Minus 35 degrees. Because at 1.32, if you just look at the rating, it is going to be minus 35 from plus 35. Why do we need minus 35? Now the refrigerated space. How much is the refrigerated space? Minus 30. If you need, like for example, in our onboard ships, how much temperature we need in meat room and fish room? Minus 20 or minus 18. If you need minus 20, then the refrigerant inside the evaporator coil, the temperature of the refrigerant has to be much lesser than that. If you need minus 18, then it should be minus 25 or minus 30. So that is how you need to just look at it. You are able to understand this? Subra, any more questions, or any clarification on this diagram? What I am showing you?
Yeah, I think that was also. Other questions were all mainly for troubleshooting. That I think
no, troubleshooting part of it. I'll come. I'll come in my second part. The second part, I thought. Troubleshooting part of it, and very often you get high pressure cutout sketch and describe. These questions are very frequently asked. I don't know. I think making a schematic diagram, I think, is very ideal for especially MEO examination candidates. That also, I have a couple of slides I'll show. Ramakrishnan, you want to ask?
Yes, sir. Sometimes in orals or normally they ask what should be the temperature of that leaving the evaporator, like 6 degrees plus superheat, something, sir, if I'm not wrong.
Yes, Ramakrishnan, see what is happening. Even the expansion valve, as I have told you earlier, internally equalized and externally equalized, how the superheat variation occurs. All those things, I have a couple of slides I need to discuss. I think since there is a lack of time in this class, I will just continue in my second session. And probably my second part will be next week, Monday, Tuesday, whenever we will inform you. That time, expansion valve functioning very clearly, we have to understand. Because today my focus was mainly on the pressure enthalpy diagram and then this part of it. And then we need to ask in the next class to start with, I will go more on expansion valve working and internally and externally equalized. That student should understand the difference between these two, and also the constant superheat business. How does it come? All of you must have seen, whenever we take provisions, have you seen? The compressor keeps on running. See, suppose you are in a port and if you have taken provision, meat and fish and all that, then what is happening? Some sort of a thawing effect has taken place to the frozen food. Then later, once it is shifted to your meat room and fish room, and when you sail out, what is happening? You will see your fridge compressor running for couple of days continuously without cutting in, because the temperatures, so much of heat or enthalpy has to be pulled out from the stuff, making it frozen again. So these are all the things we will discuss in my second part. Okay, Subra, are we?
Yeah, okay, sir. I think, sir, there's one more question in the same topic what you're covering. Why the temperature of refrigerant in the coil should be less than required temperature? That is asked by Adyan.
Adyan, okay.
Adyan.
Now, okay, now tell me, now suppose, I think it's a very simple thing to understand. Now, just look at the chart, what is in front of you. Now, in that slide, now look at the arrow. Now, here, what I'm showing you, minus 35. Now, what is this minus 35? Minus 35 is in the evaporator coil. That is inside. Then what is the refrigerated space? Minus 30. Because only when you have minus 35 here, you will be able to reach at least minus 30. So, what I have told you, on board our ships, what do? We don't, I don't think very few ships may keep minus 30. Otherwise, we generally come across minus 15 or minus 20. That is your meat room or fish room. If you want to maintain fish room minus 20, then what should be the temperature of the refrigerant? Because the refrigerant is going to absorb heat from the room to make the room cooler. From where will it absorb the heat? Unless otherwise the room temperature is minus 20, then you need to keep at least minus 25. Then only the heat will be taken, bringing down the room temperature. Is it understood? Adityan or whoever?
Yes, yes. Yes, sir.
Huh?
Yes, sir.
Okay.
Still, sir, are you going to explain the back pressure?
Back pressure, I understand we have only about, I think, 3-4 minutes. I think that requires for, in fact, I expect all the students to have a very clear understanding, because very often it is misunderstood. People keep telling me, otherwise the refrigerant, after the evaporator, with the refrigerant will go into the vegetable room, so many answers they are giving. So I want you to have a very clear idea. So let me explain it in my second part. Is it okay?
Yes, sir.
So, gentlemen, thank you very much for listening to me. And any of your questions, please send an email. And as you can see, e-feedback@himtmarine.com. And you can